Okay, so welcome back to the second talk of this morning's session. And we are very delighted to have Sami Assaf, who will be talking about positive structures in algebraic combinatorics, our favorite domain. Sami, please.
Thank you. Can everybody hear me okay? Yeah, great. So before I get started, I will mention that back in 2017, I made a bet with Igor Pag. So the deal was, so I was really optimistic about slide polynomials. They'll show up later. And I was like, I think these can be used to solve the Schubert problem. And in my sense of solve. And Igor was very, very no. So we made a bet, year and a half was a timeline. And if I lost, what I had to do was in a big room with a lot of people in this field, admit Igor was right. That was the bet. Igor was right. I didn't do it. And actually, I'll even concede that maybe slides aren't going to do it, but maybe something else. Because unlike Igor, when a problem gets hard, I don't give up and say no one can do it. So I'm going to, thank you. So what I'm going to do is I'm going to present to you a bunch of open problems. And I'm going to give you some tools that I think you can use to solve these problems. So I encourage you to try them, and I encourage you to use these tools. Also, if you want to follow along on your own, I have here, whoa, how's that moving the mouse? That's so fun. Oh, that button. Okay, so here on my website, and sorry, I don't know why the URL is so ridiculously long, but you can click on the screen and you can get the slides and follow along yourself. Okay, so here's the story that I'm going to tell today. It comes in 3 chapters, and I really love that I can walk around while giving a talk. I haven't done this in so long. I forgot you can move. So I'll dive into the first chapter on Schur positivity. So every good story starts with characters. So we're going to be talking about the Schur modules, except I'm not really going to talk about them. I'm going to talk about their characters, which are the Schur polynomials. And if you like, this is their definition, but I prefer this one. So they are the generating polynomials of semi-standard Young tableau. These are weakly increasing in rows, strictly increasing in columns. I can change every, well, can't find the pointer. I can change every number there in a box to x sub that number, multiply the numbers together, and I get the weight, right? And so that gives me a polynomial. So here's a Schur polynomial, S2, 1, 0 in 3 variables. So that's why I stuck the 0 on the end, because I care about the number of variables. All right, there's another paradigm, which is the spect modules, right? And we talked about those. They're Frobenius characters or Schur functions. They have a nice interpretation. They are permutation fillings of a tableau that satisfy the semi-standard condition. And now we can take the generating polynomial of those, well, the generating function. And for this, we're going to use Gessel's fundamental basis. It's important because it's called fundamental, also because of Gessel. Also, it showed up in work of Richard Stanley. So these are important, and I'm not going to talk about them. They're going to be my black box. So their definition is actually right there if you want to see it, but it's just Schur functions are generating functions over standard objects if I just change my monomial basis to the fundamental basis. Okay? These are the 2 different ways that you can think of Schur functions. Okay, there are other ways too, but these are the ones that I quite like. Okay, so what's our setting? We're looking for positive structures. We are trying to take these combinatorial objects and put a connected structure on them that's meaningful and nice, and lets us say, hey, that's a Schur function. And crystals are one beautiful way to do it. So these were defined by Kashiwara based on the canonical basis of Lustig. And then Kashiwara and Nakashima and Littleman gave a specific action on Tableau that gives you these edges. Loosely, a 1 edge changes a 1 to a 2. A 2 edge changes a 2 to a 3. Okay? And we have really nice structure to these objects, so they're connected, and that's awesome. What about on the other side? Well, we have dual equivalence graphs. So again, I'm putting some kind of connected structure on my objects, my standard Young tableau in this case. So what are these? Well, they're kind of due to Knuth. They're kind of due to Edelman and Green. That was the first place that I think they showed up in sort of this formulation. They're the inverse of the Knuth relations. Mark Heyman talked about them in his paper. And then I said, look at it like a graph. But everybody else had already done this. They just hadn't quite said it in the same way. So here, I need to have these compositions, these strong compositions below them so that I can get my Fs, right, associated, but there's these nice structures. So this is what I mean when I say a positive structure. It groups together all the terms in your generating polynomial into one connected structure, so that if I have something else that's written as a sum of monomials or sum of Gessels, I can try to group those terms together to realize it as a sum of Schur functions. Okay, that's the positivity that I'm after. So to do that, we need to recognize these structures. Well, hopefully you recognize these examples, because I know our attention span is shorter, but they were the same ones. But now we don't have the tableau, right? We just have the structures, and you can still recognize them. They're axioms. So John Stembridge gave us axioms for the simply laced crystals. That includes the type A one. And he said things like, well, 1 and 3 commute, 1 and 2 either commute or they do this. And sometimes lengths of strings change, but it's a specific list of 6 axioms. They're elegant, they're simple, and you can check them. So you give me a candidate for a crystal and I can check it. I have no idea what the complexity is. Yeah.
I mean, I guess I sort of think on the right that like Austin Roberts' name should also kind of be in there.
It should, and it shows up on a later slide too. But I agree. So Austin Roberts also worked on these, and on the right-hand side on the dual equivalence graphs. And we have some theorems of him coming up too. So every connected crystal has a highest weight. What's a highest weight? It's the thing at the top, right? You go up all the edges until you can't go up anymore. And there's one place you're going to reach no matter how you go up. And that is our highest weight. It's this guy right here. And its weight tells you the Schur function. That is awesome. So now I have this structure. I check it's a crystal. Yes. What Schur polynomial is it? That one, the one that I can get at the top. That's awesome. Okay, so we can't do that on the right. That's annoying. We can still use the structure on the right to great effect. And in fact, the way it first came up, Edelman and Green used it to say that their insertion rule that we'll talk about later works, and it's a good rule and it gives you all the things it should get. So if you have some kind of insertion like rule, maybe dual equivalence structure can help you prove that your rule works. Okay, even if it doesn't give you a nice formula. They knew the formula, but they use this as the machinery to prove it. So it can be a proof technique or it can help you find a formula. But really, I need you guys to do this part because I don't know how to do that. How do we get the highest weight? Is it this guy? Well, this guy kind of looks the same as that guy. And wait, maybe it should be that guy. I don't know. So that's something to think about. Okay, so point of view, that's another thing. So that was our plot, that's our goal, what we're trying to do. Now, point of view matters, right? What's your point of view? Well, maybe you think about Littlewood Richardson rules. These have come up. These numbers count multiplicities in this tensor product. But the Littlewood Richardson rule tells us we can think of it in a different way. But we could also, by the way, just take characters, and now we're doing this product. Okay, what are these numbers? Well, can crystals help us see those numbers? Well, yes, of course they can, because Kashiwara told us how to multiply crystals. And crystals aren't some made up combinatorial gadgetry, right? They come from representation theory. They're modeling, they're the combinatorial skeleton of a representation. And that's why this structure exists. So when there's something underneath the surface of the combinatorics that gives you more structure, you can hope for these sorts of miracles to happen. And it does happen here. We have a really elegant way to get this structure. Hey, I recognize this guy, right? That's S210. And this other guy is S111. And you can't know this unless I give you the weights, but it looked ugly on the slide, so I took it out. And now we have a formula. It's the number of lattice elements. That lattice condition for the Littlewood Richardson rule is Littlewood and Richardson anticipating crystals. They said, oh yeah, you got to have the ones have to pair with all the twos, and the twos have to pair with all the threes, and you can have extra ones. That's fine because you're a highest weight. And if you look at, McDonald gives a beautiful proof of the Littlewood Richardson rule in his book, which is based on Robinson's original proof. And if you read it carefully and you know about crystals, you're like, dude, he's doing crystals. And this was before Kashiwara. So these ideas were kind of in our collective knowledge, but they were made more formal with this construction. And it's just really an awesome way to prove the Littlewood Richardson rule. So what about on the other side? Well, you could also think there, so Schurs are self-dual, right? And the dual of multiplication is skewing. So can you do stuff with skews? Well, sure. And that paradigm is actually better viewed, I think, maybe, with dual equivalence. Why? Because remember, these axioms over here, right, over here are local. So what if I just ignore the 1 and the 2? And now I have to ignore edges 2 and 3, okay? Then what do I get? Well, I get a dual equivalence graph, because when you just ignore part of the structure, you still satisfy the local axioms. And that's our positivity. And now, okay, you can think about je de Takan. This is a way to rectify the shape. So you literally delete the 1 and the 2, and then you straighten everything out back to a regular shape. Well, it's amazing. So jeu de Takan works. Like you can teach 4-year-olds to do it. It's really easy and awesome. But then why does it work? Why does it not matter how you do it? It always gives you the same answer. Well, because it commutes with dual equivalence. Because dual equivalence is dual to jeu de Takan. And it somehow knows about this the same way that RSK insertion knows about the crystal and respects it. So all of these concepts, they sort of know about each other implicitly, and they can let you prove things. So if you want to prove jeu de Takan is well defined and doesn't depend on the order, use dual equivalence. Yes. Well, I don't know that I really defined it, but a 4-edge switch is a 4 with either 5 or 3. And there has to be a witness, kind of like in the Knuth sense. So in this case, the 4, who's he going to switch with, the 5 or the 3? Well, he takes the 3 because the 5's a witness that, whoa, they just jumped over top of me. So this is, and it's also a case of, I'm not giving you definitions because I'm trying to go for more of a high level, and you can drill down into the details when you want, but the idea of dual equivalence is that this edge 4 says that 4 switched with somebody, and he switched with the guy between 3 and 5, either of those two, whoever's farthest away is who he switched with. But again, the idea, and I haven't told you what a crystal is either, but these things exist, they're super nice, and I'm just trying to motivate you to learn about it, and I'm happy to give you specific readable references. And on crystals, I'll say there's a lovely book by Dan Bump and Anna Schilling that explains it for combinatorialists, but without leaving out all the good stuff from the representation theory, but in a way that combinatorialists can really just see everything, and it's very nice. So I highly recommend that for this. There's not a book here, but there are papers I can recommend. Okay, so that's it. And now we can get on with our story. So stories have conflict and resolution. So that's what we'll do. So Stanley has given us so many functions, right? I mean the Stanley symmetric functions, which are the sum over reduced words. And he originally gave it to us in terms of these Gessels. Okay, so here are the reduced words for, I actually totally didn't write down what permutation this is, but you could figure it out by multiplying simple transpositions. If you don't know what a reduced word is, that's okay. These are the objects. They have a descent set. That's a big number before a small number. That's how I'm getting these little weights down here for the F's. And we want to put a connected structure on that, but we don't want it all to be connected. We want to know that this is Schur positive. Okay, here is the first application of dual equivalence. It's from 1987 by Edelman and Green, and they define these Coxeter-Knuth relations. So you do Coxeter relations, but only the witnessed ones, and the braid relation is always witnessed. Okay, those are their rules. It's a dual equivalence structure. Their whole proof is that this is a dual equivalence graph, right? And they did it to great effect, and they said, oh, this is your high, this is the guy, wait, no, not that one. Where's the good, oh, maybe this one? Yeah, that's the good guy that they liked. But they have an explicit formula. Okay, in this case, they give an elegant, beautiful, awesome explicit formula. They have an insertion that takes this and maps it to a tableau. That bijection with tableau, they prove using this structure. But you don't need the bijection with tableau if you have the structure. That's kind of the idea. You can be a little less smart if you use more tools. So there's a monomial version of this, which is you get by doing reduced factorizations. So it's just a way of kind of separating these numbers. And Jennifer Morris and Anna Schilling gave us a crystal structure. The crystal structure is exactly, you do the Edelman-Green insertion of this guy, and that's the bijection with tableau, but what they were able to do is explicitly describe what these edges are. And they're a little complicated. Sometimes you just move a number over, and sometimes there's a funky braid that happens, and there's a pairing rule, but it's all very explicit, and you can write it down. And then you can see, oh, this guy has 2 terms in its Schur expansion. And hey, I know what the terms are. The terms are 3, 1, 1, and 3, 2. Simple, done. It's kind of awesome. It's a powerful tool. What I like about this paper is that they prove it with Steinberg's axioms, not by going through the bijection. You could go through the bijection, but it's kind of a nice application of the Steinberg axioms. Okay, so other examples. McDonald polynomials, how I love them. Okay, so they're expressed like this if you transform them and implicitly substitute them and put a tilde on top. So there's some generalization of inversion number, some generalization of major index. You're summing over permutations, so I'm getting an F expansion. Okay, this is a beautiful formula due to Hagelin that was proved with Heyman and Lohr. And there's some cases where we know stuff. I actually have no idea who this is due to. There's a crystal if you set Q equal to 0, which is doing the Hall-Littlewood case. And this MAG is the energy function. This might be due to Lescaut and Schützenberger or possibly Butler, or I have no idea. This is old and awesome. Van Leuven implicitly doesn't explicitly use a crystal, but if you read his paper, what he's literally doing is constructing a crystal. He did it in, oh, I put 2005, but I think it might have been earlier than that. I think it might have been like 95 or something. I think I might have gotten the year wrong. But he's implicitly putting a crystal structure. It satisfies all the right crystal axioms. And that's what he's doing. This solves the two-column McDonald case and gives you a nice formula. Okay, keep going. I think this is one of these wide open problems. I think it's hard, but I think we can still chip away at it. I think maybe there are some cases that we could do, possibly because Van Leuven is actually doing something for LLT polynomials, which are like a Q analog of products of Schur's. So maybe we need to just Q analog that tensor product rule for crystals. And we can do it. In this case, Van Leuven told us how. So maybe we can write that down and then try to extend it. Okay, so there's a dual equivalence story. So this is what I started working on, and this is when I defined dual equivalence. But again, I'm going to say they really came from Edelman and Green, but and it works again in the same case that Van Leuven did, right? This somehow two-column McDonald polynomials, you could just prove them in like 100 different ways. I think there are like 8 proofs. So I define these more general operators that aren't quite a dual equivalence, and I think they're Schur positive, but certainly they keep these statistics constant, which you need to factor it through, right? You want those to factor through. And Austin Roberts did this case. He noticed that actually these classes work exactly for this m equals 0 case, which is a lot harder to see in this paradigm. So it's a much different proof than this one. And then he also extended this mu1 can be 3 as long as mu2 is less than or equal to 2. So there's a little more you can push the envelope here, but it's still open. These twisted classes, I give an explicit like subset of these objects that I have the inv and maj constants. So you don't have to worry about those anymore. Are they Schur positive? I think so. Yeah.
I kind of feel obligated to elaborate a little on what I'm saying before. So the dual equivalence applications that I'm aware of rely on this locality, which is really beautiful. And the first 2 papers I'm aware that use them outside of your own kind of relied on, right? So there was an original 6th axiom, which wasn't quite local.
That's right.
And they sort of had to prove upgraded to a local version, right? So
That's right.
Paper, the other is this Schmuthoff paper.
I don't know about the Schmuthoff paper, and I'm happy to get a reference on that.
Yeah, I can point you to that. And I guess, I don't know, do you feel like that upgrade to locality is really critical to the definition of the objects?
Yes, and I think, and I'll talk about the importance of locality as we go forward, but I will say that this proof actually gives you an explicit Schur expansion for the thing, and it doesn't use the axioms. So yes, and Austin uses the axioms here when he does this case, and when he extends this case by adding another box on the first row. He absolutely uses it, and that's important. This one, no, and the formula here, it's not actually even giving a dual equivalence. It's proving the positivity by giving an explicit sum over ribbons. Yes, but I will say more because you're absolutely right. The locality is really important, but for making it more applicable. Okay, so that's still open. So McDonald polynomials, yay. I think they're hard, but I think they're worth working on. I don't think we should give up. So back to Richard, as we always go. He also defined the chromatic symmetric function of, he generalized the chromatic number to the chromatic symmetric function of a graph. This is a sum over all proper colorings. Okay, and he conjectured in certain cases it's Schur positive. And Gasharov has this like 5-page proof that just knocks it out of the park. Yes, it is, and here's the expansion. And it uses like a Gessel-Viennot type argument with this involution. It's awesome. It's so short, and you're like kind of just stunned to silence. But somehow the proof isn't quite satisfying enough. And even Richard was like, but we want to have some insertion kind of rule. Okay, well, we've kind of got that. And these machineries help us. So Kim and Piliovsky, one of our organizers, have a beautiful paper where they use dual equivalence to prove their insertion algorithm. Now, they don't quite do the whole case, but they're really close. So they have an extra condition that you have to put on the post set, which maybe isn't even needed. And then they have an insertion. They have what Richard has been asking for. And their proof uses a dual equivalence that they put on these proper colorings. And on the other side, Henry Ehrhard, who's also here, He has a crystal structure that refines the positivity. Now, again, it's only in a special case, but it's a really kind of beautiful answer in this special case. So it's refining this positivity. And for the two-part Schur polynomials, we get a Stembridge crystal. We get the kind of object that we really want. So these tools we can use kind of for any of these machinery. This is sort of what I'm trying to convince you of. Like, whatever your problem is, try these techniques because they often work. Okay, they're not completely done. So here's some more open problems, but maybe they're working on those. So maybe you shouldn't, but maybe you should. I don't know. Maybe they want help. So I recommend talking to these guys about it. It's interesting stuff. So that's it. So we've hit all the elements of a story. I guess I'll pause here for questions before I go to the next chapter. Yeah. Okay. Like type B maybe? Yes. So I don't have a general type. So if I understand Alex's question right, he's like, crystals exist in all types. Like crystals are a general construction, and I've specialized to type A for chapter 1. And he's asking, what about on the other side? What can we do? So in specific types like B and C, I have the answer. And in certain other cases, we haven't looked at it yet. And I don't know if there's a general theory of this. And that's a great question. And it's one that I think somebody should really think about. Is there a general framework for this that's similar to crystals, a type-free kind of way to say everything? So I'm going to give you specific examples and instances of these constructions in other types, but I don't have a uniform theory of it. And I think that would be fantastic to have. So thank you, Alex. And I can't believe I actually heard you because I couldn't hear you when I was sitting in the back row and you asked questions before. Yeah. All right. Okay, so chapter 2, Schur P positivity. So if you want to start something new, you should probably introduce something new. So I'm going to introduce a new character. So we're now looking at strict partitions, strictly increasing. And we're going to have the Schur P and Q functions, which you can get by specializing Hall-Littlewood symmetric functions. Here's a P. Here's my definition. So it's got combinatorics similar to Schur polynomials because I drew boxes and put numbers in them, right? What I've done is this is the shape 2, 1, and I shifted the second row over by 1. And if I had a third row, I'd shift it over by 2. I make a staircase on the left because they're strict partitions. I can do that. And now I fill numbers in the boxes, but I use negative numbers too. And the negative number didn't fit in the box, so I used a prime instead. So prime numbers are negative. And negative numbers flip the concept of row and column. So negative numbers strictly increase in rows and weakly increase in columns. Okay, these are called semi-standard shifted tableau. Also, no negatives on the diagonal for the P's. If you want negatives on the diagonal, you're really doing something with the Q's. All right, so there's a P. You might notice that it's actually a Schur polynomial. Yeah, it totally is in this one case. But in general, there's a character way to think of these. These are characters of tensor representations of queer Lie superalgebras. So all the representation theory that we wanted exists. And what about on the other side? Well, I can change this guy to an F. Sure, now I'm taking the standard things, but I'm taking signed permutations, right? So permutations, but you let the letters be negative, but again, not on the diagonal, and you follow the same rules as here. And there's a notion of descents. Here's a Schur P function. It's not a single Schur function. But okay, so we've got P's, and there's an interpretation here. So John Stembridge says that Schur P functions are characters of projective representations of the symmetric group. So all the same under the surface magic is happening. So we can hope that we can do the same things with the tools that we have. So we need to adjust our setting. So crystals exist for this type. And actually, Luis Serrano had a different combinatorial model for Schur P polynomials. And that's what these guys put this structure onto. And then with my grad student, Ezgi, we answered their question of, can you do it on shifted tableau? Yes, we can. And so we have explicit edges that we have on the crystal. And what's new here are the zero edges. In fact, without the zero edges, this construction is due to Anna Schilling. And I looked it up and I forgot it again with either 2 or 3 of her students whose names will appear on the next slide. And I'm really sorry, I shouldn't forget people's names, but it's a lot of names. Okay, so, but we have these yellow edges that Esgy and I put on there. And on the other side, do we have dual equivalence? Actually, we do. And the same thing, we get a new 0 edge. And here, the 0 edge changes the rightmost 1 to a 2. Okay, that's what the 0 edge does. And okay, modulo a few details of signs and such. And what does it do here? Well, it's even easier. It toggles the sign on the 2. There is a 2. It has a sign. Switch it. That's kind of an interesting thing it could do. Okay, so theorem, if you just erase the 0 stuff, you get the type A stuff. So this recovers a result of Worley and of Sagan that shows that Schur P functions are Schur positive. So they both did it with a really elegant insertion algorithm, but we can get it from both of these paradigms as well. Just forget about this extra 0 structure. And now you have the Schur positivity. So here we see, yeah, forget the 0 edges, it's still connected. That was the example we did before. It's a Schur polynomial. But here, forget the 0 edges and it's a disconnected. So we get a sum of 3 Schurs. And that's the example that we had previously. Okay, so there's already some interesting stuff here, but again, we're only proving old results, known results that actually have very nice proofs and don't need to be updated, but maybe we can do some more. Okay, so we need to axiomatize this. Is anyone else hearing voices? Please mute yourselves. Okay, so can we axiomatize this structure? Right, that's the next question. That's how we make the machinery powerful. We get axioms. So my student and I gave a short list of axioms that we were like, I think these do it. They use these odd Kashiwara operators, which are basically you take the 0 edge and you conjugate it by some other edges, and then you get this -1 edge and a -2 edge. We're like, yeah, this works. Well, sometimes short is too short. There we go. Gillespie, Hawks, Poe, and Schilling. It's like, actually, that's not enough axioms. So they gave more axioms that needed it, that are necessary, and they gave a sufficiency condition that's on the Schur expansion. So there's some sort of structure on the highest weights in the type A case that they put in, like, okay, now you have a characterization. But the one thing that's still lacking is like, but this thing on the Schur expansion is still a little bit not quite applicable enough. It requires a little too much thought when you're trying to apply it to other examples. So it would be nice to improve this a little bit. Look at what they did and say, okay, can we give something that's more in line with what Stembridge did in this case? Something that just doesn't require this sort of look at the highest weights and put this extra structure on them. And actually, it'd be nice if we didn't have to use these odd Kashiwara operators that are derived edges, because we don't have nice explanations for what those edges do directly. So it'd be nicer if we had a little cleaner axioms here, but still we've got axioms, so yay, +1 for us. Well, I guess for Gillespie, Hawks, Poe, and Schilling +1. Maybe it's +4, I don't know. Okay, what about on the other side? Can we characterize what's going on here? Yes, but now we get to the problem that Zach keeps bringing up, which is, okay, so dual equivalence had 6 axioms. 5 were obviously local, 1 was non-local, but actually could be said in a local way. Yeah, I don't know how to do it here. I have no idea. I kind of have some hints. So here's your homework. Fix this local axiom. I think you're gonna have to do some kind of odd Kashiwara-like thing, like conjugate this 0 edge by all the other edges and get a -2 edge and a -3 edge. And maybe that's what you need to make it local. Because you can still use it when it's not local. You can still get formulas and use the machinery, but it's a little less applicable when you have to check something that's more global, right? So it helps you with proofs, but if you already know the answer, kind of. And maybe it would be better, it could help us a little more, I think, if we could get rid of this non-local nonsense. Yeah. Okay, hang on, almost. Schur P functions we can multiply. And John Stembridge told us what these numbers are because he figured out their projective representations and he multiplied them. Okay, so these numbers are positive and we know what they are, and there's many nice formulas. Like I think there's 6 or something that I know exist, but there are more coming all the time. And we can get them from the queer tensor edge. So remember, we have a tensor product rule, and I said that those regular edges, the 1 and 2 edges, were the regular crystal things. We already know how to multiply those. So how do you define a tensor product for the 0 edge? Right? That's what we need to do. That's what we need to figure out. Well, okay, but we know how to do that. So bam, done. We can multiply this guy times this guy, which I guess I picked the same guy. So small example, but of course that's what the answer had to be, because remember it's shifted, so there's no P11. right? But okay, we can multiply them and now we get the inherent crystal structure. So that's awesome. So we can use crystals, and there are multiple interpretations using different paradigms. There's one using Serrano's model. There's one using the shifted tableau model. But any new model you have for Schur P's, you can kind of, if you can construct the crystal, you get a new formula for the coefficients when you multiply. And Zach asked about how do you skew things? Well, you can skew things, but really when you're skewing things, you're doing something with Q's. Okay, you need to keep in mind that these are not self-dual. The dual of the P's are the Q's, and the Q's are the ones that you can skew. And so there's a really beautiful theory that I would say is the type C version, and there's dual equivalence graph, and all the same theory built out. Billy Hamaker, Robertson Young did in 2014. And this is an interesting, choose your journal carefully. So my paper went on the archive slightly before theirs. They did it totally independently, have different applications. And yet there's like a 4-year difference here in the things, which is kind of interesting. So don't pick journals with long backlogs. So, okay, but instead of doing it this way, because I didn't want to define the type C stuff, I don't have enough time. But it's awesome and beautiful, and I recommend their paper. We could actually just brute force it. Let's just multiply the P's anyway. Even though I said you shouldn't, let's just do it. Because there's actually, it turns out when you try to do it, there's only one thing to do. Okay, there's one answer. And when you're looking for a needle in a haystack and there's only one, it's actually easier to find. You just move everything around and use a magnet. And this is the magnet. So this is it. There's one rule, it's explicit, and you can prove it. And it works. So again, it's a known result, but it sort of validates the machinery. It validates what you're trying to do. There's a way that we can think about what the dual equivalent should be here. But I still do think that you should rather do it this way for the product case. But powerful stuff. All right. So words. Every good story has words. So Billy and Heyman gave us the type C Stanley symmetric functions. So this guy is sort of the type C thing that I'm not talking about that shows up. You can also look at it in the work of Billy, Hamaker, Robertson, Young. And in fact, this is their application for the dual equivalence that they define is using this guy. So here's an example. You take a signed permutation, and here are all of its reduced words, because we have an S0 now, right? And then you're going to put a structure onto that, okay? But that's not quite what I want to do here. But I will point out that Billy Hamaker, Robertson, Young did exactly that. So it turns out the Coxeter-Knuth relations are exactly what you want, and it gives you the shifted dual equivalence that I haven't defined structure. And on the other side, Hawks, Paramanov, and Schilling gave a type C crystal on reduced words for signed permutations. So that was the underlying crystal that you can do on shifted tableau as well. So the story works nicely here. Let's define a type B Stanley symmetric function, which is kind of like this, only I'm going to use descent sets instead. And now I'm going to take these guys, and you are allowed to make them positive and negative, and don't make 0 negative. Okay, that's the Schur P part of it. If you make if you allow 0 to be negative, you're just recovering this. So don't let 0 be negative. That's the sort of B version of this guy. So, okay, find me a dual equivalence, a queer dual equivalence structure for this. That'll prove that that thing is Schur P positive. Okay, or go for a queer crystal on these objects. That'll prove that it's Schur P positive. Yes. Yes. On the bottom of it. See, that was that little gap that I left? Yeah. I have many more problems. I took the open problems topic of this conference to heart. So, yeah. Oh.
Peter Magyar asks, do the queer 0 arrows model a representation or an affine or similarly algebra? Do they have any representation theoretic intuition?
Yes, they totally come from representation theory, and it's not an affine thing, it's a type BC thing. But I would recommend the papers by GJ, K, and K. They have like 6 papers. One of those Ks is Kashiwara, another is Kim. I'm really not gonna be able to get all the names down in my head. But they do, it all comes from the tensor representations of the queer Lie superalgebra. So it's not an affine thing, but it does mean something geometrically or representation theoretically. Absolutely. And then to get back to Per's question, okay, there are other interesting words. There are involution Stanley symmetric functions where we use involution words. There are fixed point free Stanley symmetric functions. So for these, Eric Marburg, Zach Hamaker, and Brandon Pulaski, I really shouldn't forget, have done a lot of work on these things, and their insertion ideas, their graphs. Hiroshima is another person who constructed what he conjectured was a crystal, I think, for these guys, and then Marburg proved that it is in fact a queer crystal. So there's lots of work, there's work in progress, and there are lots of things like this. And keep this in mind, Stanley's symmetric functions. We're going to revisit those in a minute. But there are lots and lots of applications, and there are more, but finite time and all. But lots of applications. So when you find a friend who you think is sure P positive, try these techniques. And if you need examples, right, we're mathematicians. We look at a bunch of examples, we extrapolate, and then we generalize, right? So there are tons of examples. So the proven things I've given you are your homework for reading, and then the exercises are the open questions. Okay, so any questions on this? Okay, let's change our paradigm again. So again, I'm not telling you about the type C thing. I really like it. It's awesome. There's so many more problems there, but I want to tell you a different way to generalize. Okay, that's not going to a different type. And by the way, all this is open for type D. So if you want to forge some new ground, go to type D. Also for affine, go there. I'm going to go somewhere else. I'm going to trim it. Sometimes you have to kill your darlings and cut your story a little shorter by cutting characters. So that's what we're going to do. So what's a Dimitrov module? Well, I'm not quite going to tell you, but basically what you do is you take an extremal weight space. So that is a weight space that the weight is a permutation of the highest weight. It's going to be one dimensional. The Weil group acts on it. This again is a general construction. It works in all types. I'm focusing on type A. So then you let the Borel, so upper triangular matrices, act on that, and you get a submodule of your irreducible module. It's a B submodule. Okay, B is the Borel, upper triangular matrices. We can take its character. It's a Dimitrov character. Why am I indexing it with a weak composition? Because I'm taking the weight from the weight space. Let W act on lambda. Well, I mean, you could have taken multiple W's that act the same way on lambda, right? So this avoids that redundancy, and it's a nicer way to think of it. There's also the isobaric divided difference operators also generate these if you want to write the character down. Okay, but I want to do combinatorics. So I couldn't not mention Kronecker diagrams. I'm so obsessed. I'll cop to that. But the model that maybe is the most pretty for this picture and kind of works very elegantly is the semi-skyline augmented fill-ins by Sarah Mason, which I should have called this object A, because then I would be able to get my name in the slide, but I didn't think about that in time. But these are due to Mason, and she studied these a lot, and they're going to come up repeatedly. So they're kind of like Tableau, but they're more like reverse Tableau. You want a weekly decrease in the rows, and the columns aren't strict in that they don't like increase or decrease, but you sort of have a triple condition, right? A la Hagelin. He loves his triples. And then there's a flagged condition. This guy's vanished because there's a 3 in row 2. A 3 can't be in row 2. 3 is too big. So that's the flag condition, which is like the upper triangular matrices condition, right? So we get a part of a Schur function. It's a 5-dimensional submodule of this 8-dimensional arrow. Okay. All right, and it's a generating function of them. Bam. What about on the other side? Well, if you wanted to use Kronecker diagrams, which you totally should, there's a quasi-Yamanuchi version. Sorry, that's a mouthful. I don't know what we were thinking. So this is with Dominic Searles. We came up with these, but and then it's mostly this combined with Sarah's paradigm gives you these key tableaus. So maybe those aren't due to me. Maybe they're actually due to Searles and Mason. But you just shift your paradigm a little bit. We're basically taking these rules and we're just putting standard objects in, and we're ignoring the triple condition. Or sorry, no, we use the triple condition. We're ignoring the flagged condition. And now there's this concept of a weak descent set. Okay, and you can see this sort of vanishing thing comes up here. This doesn't have a weak descent set. It vanishes. It gives you a 0 when you try to do the polynomial version. And here are these infamous slide polynomials. Here they are. They're defined by myself and Dominic as a polynomial generalization of Gessel's basis. Okay, and that's what we use as our black box over here when we're doing the standard paradigm. It's these slide polynomials. Okay, so this is kind of like our original story. We're not doing a different type. We're still in type A. We're just doing a different thing with it where we care about the action of the Borel. Okay, so the representation theory is still here. It's still working for us. And the structure is still here. But well, we have characters are still here. We need the structure, right? So what can we do? Well, there is a crystal on Tableau. There is a bijection between these objects and Tableau. So we could just do the crystal and then just erase the stuff. And actually that already is known. Dimitrov crystals exist. They were conjectured by Littleman and proved by Kashiwara to exist. And there's a sort of reduced word construction. Now, if you want to do them on these objects, Anna Schilling and I can tell you exactly what they do. So here, the one edge changes a 1 to a 2. Okay, well, sometimes it has to flip the column. Although if you use Kronecker diagrams, you wouldn't have to flip the column because somehow the Kronecker diagrams know about that flip and they don't mind. But in this, okay, but we can tell you exactly what to flip. Okay, so there's an explicit model that we get here. And it's nice, it's a truncated crystal. That's not so bad. What about on the other side? Well, this is interesting. You do the exact same thing. In fact, under the bijection of these with standard Young tableau, they're in bijection with standard Young tableau. It's literally the same edges. There is nothing different. I mean, if you describe them, okay, so here I should be changing, this says change a 3 with a 2 or a 4. And actually I kind of cyclically rotated, but really I swapped the 2 and the 3, and then I sorted out that column with the 4. So again, it's a sort of sorting out some column stuff that happens. But it's the same thing, but we can see the truncation happening again here. This guy vanishes. And now we have these weak descent compositions, so we have zeros involved. Okay, so it's a little more subtle, but the structure is the same. It's literally the same. But what about the axioms? Well, now we have a piece of a crystal. So how do you know you have a good piece? How do you know you just didn't cut things in some kind of funny way, right? And give the crystal like a really bad haircut. It's like, doesn't mean anything. It's kind of nonsense. So I threw this problem to my grad student, Nicole Gonzalez, and she knocked it out of the park. So the extremal condition is easy. It says that you can't take part of a string. You either take it all or you don't get any of it. And then there's a couple other axioms, very much like Stembridge's axioms, that you have. And now you know you have a de Major subset of your crystal. So axioms exist. We know how to recognize these objects when we're giving them abstractly without knowing what the vertices are. What about on the other side? Well, it's just a dual equivalence graph. But, well, how do we prove anything? Well, you replace this local Schur positivity condition with a local de Major positivity condition. But here, notice I changed my example. I don't know if you guys noticed that, but previously I had this of length 3. And so the reason this guy was dead is because he wanted something here and there wasn't room. I need to have room for everything to show up. Otherwise, the axioms don't hold. But there's some stability arguments that you can use for your favorite family of polynomials. If you're using, for example, I don't know, maybe you like Schubert polynomials. They also have some stability, so you can still run this machinery for them or for the de Major characters. Anything that sort of stabilizes in a nice way where you can make these zero terms show up again. Okay, and then you can kind of pull it back. But there's definitely a subtlety here that's a bit of a hiccup. In the type A case, there's a relationship between Stembridge's axioms and the dual equivalence axioms, okay? And you can go back and forth. The one implies the other and the other implies the one, okay? Can we do anything like that here? And actually, could maybe understanding this truncation and these axioms help us get around this problem of we have to be able to stabilize? Because that's kind of an annoying problem. We don't want to have to do that, right? That does limit our applications. I just said it doesn't, but it does. So, okay, let's try to get around that. Maybe come up with a dictionary between these two. Also, what is a de Major queer? I'm not sure what order to put my adjectives in, but do this for the case we just did. Okay, truncate the queer crystal. I don't know how, but okay, we have a queer dual equivalence graph. Okay, can we just do the same theory here? Now we're getting some sort of de Major P thing. Okay, maybe this matches up with some geometry. It does. Maybe it matches up with some representation theory. Not so sure on that one, probably. But we could try to do the same game, combining these two ideas. Okay. And I'll give you some examples to try it out on in a minute. So Mathieu gave us a way to multiply, to tensor a de Major module. So this guy's a de Major module. This is a full irrep, so a full irreducible. And we can tensor them together. And it has an excellent filtration. If there's a filtration where here the successive quotients are de Major modules. They're isotypical de Major modules. Okay, that's what an excellent filtration is. If you're familiar with a good filtration, that's the same thing, except this is now going to be irreducible. Okay, so good filtrations are not in the de Major case. Excellent. Now we know we're somewhere is in the de Major case. So here's a really awesome proof. So you can take these semi-skyline augmented fillings and you can do RSK insertion of a tableau and it gives you the right answer. And in fact, Hagelin, Luoto, Mason, and Van Willigenburg have an explicit combinatorial formula for these objects that look very much like Littlewood Richardson tableau. And their proof, because it works with RSK, and RSK knows about and totally digs the crystal, what that's saying is we can truncate one of these factors, that's this guy, and we still get a Dimitrov crystal, because look, this guy's a Dimitrov crystal, it's this one. And this guy's a Dimitrov crystal, it's this one. So the product structure still works. So again, we're getting a lot of mileage out of the machinery that's already built in here coming from the representation theory. But their proof doesn't rely on this. I would say that this picture is a corollary to their proof and the fact that they use RSK to such great effect. Okay, what about on the other side? Well, again, these are local conditions. So let's try the same thing and ignore things. Now remember, we did this reverse thing, like reverse condition. So instead of ignoring 1 and 2, we ignore 6 and 5. But it's the same kind of game, only it's a little more subtle over here, because it matters that I skewed out these two. I can't just skew out 2 random things on the edge. I have to skew them out from the top. Okay, and then everything carries through and it all works. So we have a notion of these skew Dimitrov characters. But are these the same? I actually don't know. Here's a good question, and maybe Per, because he is a whiz on the computer, could answer this in like 5 seconds. So maybe like it'll be closed soon, but maybe the answer is no. But I feel like these numbers are related. They might actually be the same. So on this side, we are multiplying a Dimitrov character times a fully irreducible, so times a Schur polynomial with the same number of variables. That'll be important. And over here, we're skewing a Dimitrov character by a partition kind of at the top. And we get some expansions, and are the coefficients the same? I don't know. And if they are, well, I mean, you understand the questions that will follow, right? If they're the same, there should be a reason. And maybe this relates to relating these two constructions. Yes. It's dual equivalence. It's the same graph, but now we have weak compositions indexing our objects instead of strong. And then everywhere you see Schur function, you replace it with Dimitrov character. More or less. So yeah, here's something the computer could maybe help you check if this is a stupid question. I should have checked it before, but Maple wants to charge me another $1,000 every year. So, and Sage doesn't tell me how to do this yet. So all of you Sage people, please help. Okay, so Igor says, why do we expect things to be positive? He's right. Don't have unrealistic expectations. When I multiply 2 Dimitrov characters, it's not always positive. They do not have positive structure constants. These are a basis for the polynomial ring with non-positive structure constants, right? Positivity doesn't happen just because you want it to. All right, so this is a problem. Now, notice the difference in this example and the one on the previous slide. Let's look back. Okay, maybe we can't. Oh, we can. Great. Here, notice 0, 0, 1. 0, 1, 0. This is different. This is a Schur polynomial in 2 variables. That's the problem. It is a Dimitrov character. It's not a full irreducible, not for GL3. Okay, and I get negativity, and that's a problem. But when this happens, remember that there are miracles happening below the surface. You just have to understand what's happening below the surface. There's representation theory here, so let's lean on that. So Polio conjectured that when you tensor 2 Dimitrov characters, you get a Schubert filtration. It looks exactly the same, but here I changed from V to U. Okay, this is a minimal relative Schubert module. It's a submodule of the Dimitrov modules. Okay, so there is something to look for from the representation theory, but how do we understand that? How can we come at that? Well, I gave this to another one of my students. Every time I give them problems, they solve them. It's kind of awesome. That's why I'm hoping you guys will take it up. It's like I have like 200 students now. Awesome. More math. So Dan Joseph Quijada and I were like, hey, can we do Monk's rule? Can we do a Pieri rule? And yes. And that's like a 60-page paper. It's kind of long. And then I generalized that during COVID because what else was I going to do? And I generalized it to the case of you take any Dimitrov module, you take any Schur polynomial. It can have the wrong number of variables. Okay, it can have not enough variables, and we get an explicit insertion algorithm, which is not RSK. RSK does not work here. You have to change it. to a union that is not disjoint. It's a lot of negativity for a positive talk. But it's not disjoint, but that's okay. Not being disjoint is not a problem. We still have positivity here. These are explicit. And now this set, and again, I had to use the Kronecker diagram model. I couldn't get this to work with the semi-skyline augmented fillings. It would be kind of cool to see if there's a nice way to say this with that model. That's open. But here I use the Kronecker diagrams and I do this insertion and I get a union of Kronecker diagrams. The union of these two things is not disjoint. Their intersection is exactly this. So the negative signs come from inclusion, exclusion. That's combinatorial. We get that. We can do that, right? We know about derangements. So it's no harder than that. So now we understand the positivity. And I will say on a character level, I don't know if I put this on the slide or not. On a character level, this is a de Major character times a Schur polynomial. It's a positive sum of atoms, of de Major atoms. It's also stronger than that. It's a positive sum of Schubert characters, but I think I won't get into that. Okay, so don't do this. We're working on this. I think we almost got it. But you could do this. Yes. That one? Yes. You're very good at knowing what the blank spaces are. Thank you for. So here's an open problem. Do better than this. Like COVID's not over yet. There's still time for more math. Sorry, that was more depressing than it was in my head. Let's try to get it to work in general. These are going to be explicit non-negative integers. They have a Littlewood Richardson flavor. I'll tell you kind of what they are. You take a composition diagram, a key diagram, and you add some bubbles, and then you put numbers in those extra bubbles, and the numbers satisfy some conditions. And they have to be lattice, and it's the same lattice condition that you know and love from the Littlewood Richardson rule, which is really telling us that crystals should be able to kill it on this problem. But dual equivalence, can it do this problem? I think it should be able to. It can do a lot. Okay, so good stories always leave you with more questions, right? So you can kind of do the sequel. So here are some sequels. So don't be intimidated by this. We're going to ignore this, okay? But there are non-symmetric McDonald polynomials. These were introduced by Optum. They generalized by Trednik to all types. So again, anything that we can do in all types is kind of exciting because there's so many more problems. But in type A, we get this really beautiful formula. It's beautiful, especially when you kill the t. Okay, so this is written in X's, the monomials, and I really dig the slides, right? So we can rewrite it in terms of slides, right? That's a theorem. It's not a hard one either, but we can rewrite this in terms of slides. And by the way, when we set t equal to 0, here's what you're going to notice. This is dead. This is 1. We can ignore it. So that's why we set t equal to 0, because then we have something that's friendly. Like that, I'm okay with negative numbers. I'm not okay with fractions. They still scare me. Okay, so here's a theorem. There's a weak dual equivalence on these objects. So interestingly, I came up with this construction the same time that Per Alexanderson and Mahoney. What? Mitab. Okay. So they came up with a conjecture and they were constructing an insertion algorithm that literally could do this. So they were kind of doing the other side of this at the same time. But we get positivity. It's a positive sum of de Major characters. Who knew? Well, I mean, McDonald's are conjecturally positive sums of Schurs, so maybe we knew. But it's kind of nice that what's happening in type A, in the regular unpolynomialified version, we can see it happening here. And maybe it's even easier. I don't know. But okay, but as I said, that dual equivalence, okay, I will cop to it. It doesn't give you nice formulas by anyone's definition of nice. Okay, it's the number of connected components. It's the number of equivalence classes of this type. That's not a nice formula, right? But crystals give you nice formulas. So Nicole Gonzalez axiomatized de Major crystals exactly so that we could do this. We gave a crystal structure for these guys. Now we have a nice formula. We know explicitly what these objects T that we're summing over are. And so we can get this formula. So that's the advantage of crystals. I feel like this proof was much easier, okay? But this theorem is much nicer. So, you know, you got your points of view, pick one and go with it. Here's another thing that we did. So Sanderson proved and sort of sparked this whole work of Bogdan Ion on these this specific specialization of non-symmetric McDonald polynomials, it turns out that this guy, Sanderson proved, this guy's actually an affine de Major character. It's one affine de Major character. Every affine de Major character shows up like this. Okay, so, well, we had a crystal. Can we make it an affine crystal? Sure we can. And now we have a model, an explicit model for affine de Major characters using the combinatorics of McDonald polynomials. And what this shows us, there's an affine edge, it's a zero edge, not like the queer zero edge, it's a different kind of zero edge. If we delete that zero edge, then we're left with the finite case. That tells us that an affine de Major character has an excellent filtration. And everybody I've talked to says, oh yeah, that's true in general. And nobody can write down a proof. And so anybody who says that this is obvious, please, can you prove it? Please, this is not sarcastic. I'm not making you a bet. I'm just asking you nicely. I would like to read it. Please, may I have it? I really think that would be an interesting one to see. Like everybody seems to think it's true and that it follows for natural things, but okay, I believe you. Please write it down. So I would like to see that. But anyway, it gives us hope that, hey, can we just do everything affine too? Sure, why not? So many more problems. Okay, so let's go back to Schubert polynomials. Well, I guess we haven't gone to them yet. Let's go back to Stanley symmetric polynomials and let's truncate them. What do we get? A Schubert polynomial. So here's a Schubert polynomial. It's a sum of reduced words of slides. This is why we came up with slides. Well, actually, here's the funny thing. I didn't know about this formula when we came up with slides, or we could have done it in a much simpler way. I only knew about pipe dreams. I was kind of new to Schubert's then. And so we used it as pipe dreams, but it turns out that actually we're just kind of taking this expansion here inside here, thinking of it without the words, and now we get slides and they multiply. And you know what? Schubert polynomials are positive sums of de Major characters. This was known to Lascaux and Schutz and Berger. It was proved by Reiner and Shimizono. I guess Lascaux and Schutz and Berger sort of said how the proof goes, but I feel like the details were in the Reiner-Shimizono paper where they give like, I don't know, give like 5 proofs of this or something. Okay, how can we see this? Well, remember what we did with Stanley symmetric functions? Well, if you truncate a Stanley symmetric function, you get a Schubert polynomial. And if you truncate the more Schilling crystal, you get a de Major crystal. That's the same statement, but crystallified. If you do Coxeter-Knuth relations and you take the weak descent composition, then you get a weak dual equivalence. So everything that worked before, the exact literal same thing still works. It's no harder. Okay, well, there are other Stanley symmetric functions and they give you other Schubert things. So what about type B, type C, involution, fixed point free? Some of these are done. Talk to Zach, probably. He would know which ones are done and which ones are open. But we can truncate all of these structures that we have for the Stanley symmetric functions, and we can get positive statements about these Schuberts. And now, remember, the optimist in me can't, I wasn't going to mention it, but I got to say it now. Remember how we're kind of figuring out how to multiply keys? And hey, look, ooh, I don't know. Maybe it'll help us multiply Schuberts. I'm not going to bet money on it, but I will publicly admit that I'm wrong when I decide to give up. Thank you.
Okay, thanks, Sami, for a very, very interesting talk. So are there further questions? Yes.
Maria.
Whichever, go ahead.
That's a great, so I didn't know, but I haven't been reading the archive. I should. I missed that paper. I'm super excited and I will go look at it. I'm not sure. I think in general, these problems come up naturally because they always come up from the representation theory context. I can't really, I'm really excited by, I'm excited to go read that paper. Thank you for letting me know about it. I can't really say much more. But yeah, look for lots of other problems. But I would say that before you start taking my word for it that these problems are open, I mean, this conference was announced 2 years ago, so I know they were all open then. I did update. I think some of them are still open. I think most of them are still open, but you should check. That's cool though. I didn't know about that. And Sam had a question.
Can you go back to the link for your slide?
Oh man, that's like at the beginning. It's okay. There. Just click the screen. And it's the friendly version where it doesn't have the overlays. Yes.
Either crystal or fluid that can improve Schur positivity or other specialization other than
Probably.
Could we repeat the
So,
question?
oh, sorry. So the question is, can crystals or dual equivalents help you with Schur positivity for other McDonald polynomial specializations of McDonald polynomials? So if you set either T or Q equal to 0, then that's done. The 2 columns plus an extra box that Robert's added, that's done. 3 columns, Jonah Blasiak has a formula. He has a proof of Hagelein's formula for 3 columns, but there's not a dual equivalence or crystal structure for that formula. But maybe using that formula could help you derive one that would maybe then extend. So Mark Heyman used to tell me that if you can do 3 columns for McDonald polynomials, you can do it all. But maybe that's not quite true, but maybe it is as long as you do it in the right way. So maybe that's worth looking at. I don't know any other, I know there, I have okay. Well, I also did the case where you have 2 columns and 1 really long row. It's not a dual equivalent and it's not a crystal, but there's an explicit formula for 2 columns plus a really long row. Maybe you could turn that into a dual equivalence or a crystal. And again, then maybe that generalizes. In fact, if you combine that with the 3 columns, maybe that's where to go. I'm not sure, but I think combining these other things that are working in new ways, and if you start building out this machinery on it, there's a chance that you could extend it. Alex.
Actually, I don't have a question, but your talk reminded me of open problems.
Oh, please.
Okay, so one problem, like you have a way for this.
Well, I mean, I don't want to give a big speech. So there were 2 big themes. One theme is like what you were talking about. The other theme is cluster algebras. There were a lot of talks about this, and kind of philosophically, how to connect these 2 topics. But let me be a little bit more precise. There was a question that Zelevinsky asked me like a long time ago, and maybe, I don't know, it's like half open, but let me mention this topic. So suppose you want to calculate Littlewood Richardson coefficients for type A or for any type. And one way to do it, as Sami was explaining, is to use crystals, use Kashivara thing, or you can be more explicit if you use Littlewood path model. There is another general method how to calculate Littlewood Richardson coefficients is given by Bernstein Zelevinsky. They said it's the number of lattice points in some polytop. So question is how to connect these 2 things. And there are some connections. For example, Kronecker, like in his talks, so he was talking about these MV polytopes, which are kind of related to both worlds. But I would like to see something more explicit. So namely what Bernstein Zelevinsky says, that it says that C lambda mu equals to number of lattice points in some polytop. What Littleman paths say, it's equal to, there are like several polyhedral pieces. So it's sum over several polyhedral pieces of the number of lattice points. So can we actually, cut busy polytops into some pieces, which are can be transformed into Littleman, pieces. So how do they're so that's one question. Yeah. So there's another question which is also related to crystals, and okay. So it's also probably related to future talk by Alan Knudsen. So actually yesterday we were talking with Alan after in the evening. So there is some fusion ring or quantum cohomology ring. So some kind of deformation of usual cohomology ring of the Grassmannian, and one would like to get a structure constants for this ring. And these structure constants are known. I don't know if Alan will explain it in his talk or not, but there are like, yeah, okay, so probably you will know how to calculate these structure constants using puzzles, which very nice, an explicit rule. But I had another like approach in mind, which is still not kind of, so basically I want to see a rule which is kind of similar in spirit to what Sami was talking about. Can we actually construct a crystal? So basically, once you get a construction of crystal, you get coefficients so for free. So can we actually construct crystals on some class of tableau? And these tableaus are known. There are some cylindrical tableaus. Can we describe crystals that satisfy Stanbridge axiom? So once we do it, like as Sami was explaining, you can get all these coefficients for free. So that would be kind of, I don't know, maybe somebody already solved these questions, but that's, yeah, so, okay, thank you.
Yeah.
Is there any reason you can't skew
Is there any reason you
the
can't skew the shifted? Well, it doesn't make sense to skew a Schur P polynomial. You can, but you get nothing that's positive. Because a skew Schur P is not a positive sum of Schur P's. So you could look for positivity there in some other form, and that would be interesting. But the skewing and products are adjoint, and P's and Q's are dual, right? So when you skew the Q's. But well, when you multiply the Q's, you do get something that's P positive. Do you get something that's Q positive?
Yeah.
I guess you would, because you have lots of twos. Yeah, because you have a ton of twos. Yeah, but it's sort of, it's probably off by a factor of 2 then, right? Of the P's.
You just have to divide by the appropriate factor.
Right, the appropriate power of 2. So multiplying Q's is, so Schur Q functions are 2 to a power times Schur P functions. Okay, so if you multiply P's, it's positive in the P's. So if you multiply Q's, it's going to be positive in the Q's because you're just multiplying those powers of 2 together, and that's still a power of 2. And it works out. So I guess you could do it that way, but I don't know that. Yeah, I'm not sure. I think it's an interesting question. I sort of dismissed it because you don't skew the P's, but maybe you should. I'm not sure what you get per. I had a question. That's right. So just to repeat it, Per is pointing out that you can skew the symmetric McDonald polynomials, and it still has the same positivity conjectures. And in fact, in the case where you have a dual equivalence, you can prove it because dual equivalence skews nicely. But if you had dual equivalence in general, maybe you could prove more positivity in general. Is it? Yes. That's a great question. So Per is giving us more problems. I love it. More problems of skewing the specialized non-symmetric McDonald polynomials, which are affine de Majorque characters. Why not skew those? And that's an awesome thing. Yes, please, someone do that. That's awesome. Yeah. And I would expect that the same sort of things would work because skewing should work because we have the dual equivalence. So I would be more interested in someone taking that dual equivalence and then turning it back into a crystal so we can get a nice formula, because especially in that case, we don't get the super nice formula from dual equivalence. That's a great point. Yes, Vic. Those are minimal relative Schubert modules. So there are some really awesome lecture notes that are so terse by van der Kallen that it's called like Frobenius splitting of Schurs. And that actually gives you an English version. Most of the papers I cited are in French, and luckily, one of my postdocs, Anne Dranowski, is French, and she was able to read it to me, but the Van der Kellen notes are in English. So if you don't speak French or read French, those notes are really good, and they have all the details of the minimal relative Schubert modules.
Any other questions from the audience here? Okay, well, let's thank Sami again.